Now we go for question number 25 about potentiometer. Potentiometer. My dears, this is very important theory. Pay your very nice attention on the screen, please. First of all, let me give you introduction of potentiometer. What is the introduction? Potentiometer is that electrical device with the help of which not only we can change the potential difference, but we can measure it also. Such a device is called potentiometer. It is superior to rheostat. Why? Because in a rheostat, we can simply change the potential difference, but we cannot measure it. Here we will see, using potentiometer, we can measure the potential difference. Not only we can change it, we can measure it also. Correct? That is why it is superior to rheostat. How? I am showing you. Before we go for construction and working principle of potentiometer, I would like to make you convinced with the necessity of a potentiometer. My dears, all of you have heard one proverb. And what is that? Necessity is the mother of invention. Necessity is the mother of invention, correct? Without the necessity, nothing is being invented. Then here, what was that necessity because of which we were inspired to prepare such a device? Let us see that necessity now. Suppose I have one battery, correct, whose EMF is E, whose internal resistance is R. Because this resistance is internal resistance, I am putting this box so that you will find this resistance inside the box, that is internal resistance of the battery. Okay, fine. Now I want to measure this EMF of this battery using some table voltmeter. Now what is voltmeter? How it is constructed? How does it work? Everything we will study in the next chapter. At present, you simply remember it is that sort of instrument with the help of which we can find out the potential difference or voltage. Correct? Fine. Now what do you mean by table voltmeter? Table voltmeter is simple dial type voltmeter which you are using in the laboratory. It is called table voltmeter. Okay? One such a table voltmeter we have, and we want to measure this EMF using this table voltmeter. That's why we have connected across the battery. Correct? The positive terminal should be this one, negative should be this one. I am showing. Positive terminal of voltmeter should be connected with this positive terminal of battery, and negative terminal of voltmeter should be connected with negative terminal of the battery. A and B are the two terminals of this battery. This one is positive, this one is negative. Fine. Now, where will you show direction of current? Always away from positive terminal of the battery. Correct? In the outer part of the circuit, direction of current is from positive to negative terminal of the battery. So direction of current is like this. Right now, let it be capital I. In any single loop, remember the current flowing through each component will be same. Let it be I. Now this current, when it passes through this voltmeter, it gives some deflection. I mean the pointer gives some deflection. You can just take the reading. You can find out how much voltage is measured by this voltmeter. That is its reading. I am writing here, reading obtained in the table voltmeter while measuring EMF. Correct? Tell me, voltmeter will read voltage between which two points across which it is connected? Here this voltmeter is connected between A and B. So it must read voltage between A and B. So I am writing here VAB, that is voltage between A and B. Correct? But what are A and B? They are terminals of a battery. So voltage between terminals, it is called terminal voltage. It is shown by symbol capital V. And because current is flowing away from positive terminal of the battery, this battery is getting right now discharged. And for a battery which is discharging, then you know the relation between terminal voltage and EMF. Don't you know? Last time we had seen V equals to E minus IR. V equals to E minus IR. correct? Tell me, right now some current is flowing, then only you are getting some deflection, correct? Otherwise you will not get the deflection. So right now some current is flowing, meaning thereby I is not 0, and every battery has got some internal resistance which is never 0. So small r is not 0. Neither I is 0 nor r is 0. I mean to say this term is not 0. If this term is 0, then V is equal to E. But right now this term is not 0, so V is not equal to E. V is not equal to E. Correct? Tell me, for what purpose you had connected this table voltmeter across this battery? To measure its EMF. To measure its EMF. But tell me, have you got reading? Have you got reading equal to EMF? No. Reading obtained is not equal to E. Reading obtained is not equal to E. Meaning thereby, EMF of a battery cannot be measured accurately using table voltmeter. And if you try to measure, then there will be an error by this much amount. Your reading will be less than expected by amount IR. Correct? Fine. Of course, that reading is equal to terminal voltage. Reading is equal to terminal voltage. So terminal voltage can be measured accurately, but so far EMF is concerned, it cannot be measured accurately using table voltmeter. Then tell me what to do. Using table voltmeter, we cannot measure the EMF of a given battery accurately. Then what to do? You have to prepare one such a device with the help of which we can measure the EMF of a battery accurately. My dears, that very device itself is potentiometer, and we will prove just now that using potentiometer we can measure EMF of a battery accurately. Okay? So the job which could not be done by table voltmeter, same job can be done using potentiometer, meaning thereby potentiometer is also superior to table voltmeter. Potentiometer is not only superior to rheostat, it is also superior to table voltmeter. Correct? Fine. Now we go for construction and working principle. At present, you please consider only this part of the circuit. Look here, only this much. Only this much. Okay. At present, you don't see this. You just consider this part of the circuit, which is called primary circuit. Primary circuit. That gives you construction of a potentiometer, in which you will find one battery with negligible internal resistance, one resistance box, one long straight uniform conducting wire made up of, as I said, constant ton. Then we have one key. These all components are connected one after another, okay, to form a single closed loop. This is nothing but potentiometer. Fine. Now, the current starting from positive terminal of the battery, I am showing by symbol capital I. Okay? That current will flow through R also, through the resistance of this wire also, it will flow through internal resistance also. Correct? Fine. For this wire, resistance per unit length, I just take it rho as per the textbook. Okay? Better if they could have used symbol here rho dash, different than rho, because if we use the symbol rho, somebody will be misguided. He will understand that this is resistivity. No, my dears, resistivity is not the resistance per unit length. It is resistance per unit length and per unit cross-sectional area also. Right now, we don't have to mention anything about cross-sectional area. This is not resistivity in short. Please remember, this is not resistivity. It is simply resistance per unit length of potentiometer wire. Okay? Don't be misguided. Though I am using the symbol as per the textbook, it is not resistivity, it is simply resistance per unit length. Its unit is ohm upon meter, correct? Fine. Now, for this much length, let it be capital L. This much length of the potentiometer wire, let it be capital L. For unit length, if resistance is rho, then for L amount of length, what will be total resistance? L into rho. Here it is, L into rho, correct? So total resistance of this potentiometer wire from here to here, let it be capital L into rho, correct? For unit length, resistance is rho. For L length, it will be L into rho. Fine. Now, let us apply Kirchhoff's second law in this closed loop in the direction of current. In the direction of current, let us apply Kirchhoff's second law, correct? That is sigma IR equals to sigma E. Come on, go this way in the direction of current. Take the product of current and resistance, minus IR. Here it is, minus IR. Go ahead in the direction of current this way, from positive to negative in the direction of current. Current is I, resistance between these 2 points, that is resistance of entire potentiometer wire, which is L rho. Take the product of current and resistance, come on, minus IL rho, minus IL rho. Why minus sign? Because our journey is in the direction of current. Go ahead. Now minus I into small r, minus I into small r, correct? How many such terms you will get? Equal to number of resistances. There are 3 resistances right now. One is the resistance kept in the resistance box, another is the resistance of potentiometer wire, third is the resistance of, that is internal resistance of this battery connected in primary circuit. Fine. So we are getting 3 terms, and that equals to sigma E, algebraic summation of EMFs. Come on, go this way again, and when you go this way, this way, this way, the terminal coming first in the way is negative, that's why minus E. Look here, minus E, correct? Multiply the whole equation by minus 1, then all the minus terms will become plus, and then after you can just take I common inside the bracket, R plus L rho plus R, R plus L rho plus R, and when you multiply minus 1 here also, it will be plus E, correct? Find out I, it is E upon R plus L rho plus R. What is this? Current passing through potentiometer wire. Wait. Just select one point, say point C1, which is at distance L1 from positive end of the potentiometer wire. Now these 2 points are separated by distance L1. The potential difference between those 2 points I am taking VL1, VL1. That is potential difference between those 2 points which are separated by distance L1, and those 2 points are A and C1, A and C1, okay. What do you mean by potential difference? It is also called voltage. According to Ohm's law, V equals to IR, V equals to IR, that is voltage equals to current into resistance, current into resistance. Current is I, correct, into resistance of this much length of the wire, right? At present we have considered this much length, okay. Resistance per unit length is rho, then for L1 length it will be L1 into rho, L1 into rho, here it is, L1 into rho, correct. Current into resistance will give me voltage. What is the value of I right now? Formula for I is right now E upon R plus L rho plus R. Come on, I is E upon R plus L rho plus R into L1 rho, into L1 rho, correct. Take this rho inside, correct, and it will be E rho upon R plus L rho plus R, E rho upon R plus L rho plus R into L1, correct. Now in the given conditions of a potentiometer, all these quantities are constants, and so this bracketed quantity can be taken as another constant. So I just replace this bracketed quantity by another constant, let it be sigma, okay, this L1 as it is. Only in place of bracketed part I have written sigma. My dears, here also don't be misguided. Though I am using symbol sigma as per the textbook, it is not electrical conductivity, no. It is to be given a specific name, and what is the specific name? I am showing you. Find out sigma from here, transfer this L1 here. So sigma will be VL1 upon L1, sigma will be VL1 upon L1, VL1 upon L1, and if you take L1 here, correct, the denominator of VL1, then you will get VL1 upon L1 as this much, correct. In place of this bracket only we had written sigma. So sigma is as good as E rho upon R plus L rho plus R, correct? But what is E upon R plus L rho plus R? It is nothing but I. So in place of this part, I can write I. In place of E upon R plus L rho plus R, in place of E upon R plus L rho plus R, I can write I, this rho as it is, correct? So remember, this sigma has three formula: total voltage upon total length, or E rho upon R plus L rho plus R, or I into rho. Now this sigma is given a specific name. It is called potential gradient. What is it called? Potential gradient. Then you may ask why the name is like that, potential gradient. My dear sir, it is very simple to understand. It is total voltage upon total length, that is voltage or potential difference per unit length. Potential difference per unit length. Just recall two words from 11th standard. Did you study about velocity gradient? Yes, in 11th standard. What was that? Difference in velocity per unit length or per unit distance. If difference in velocity per unit distance is called velocity gradient, difference of temperature per unit distance is called temperature gradient. Similarly, difference of potential per unit distance should be called potential gradient. That's why the name is potential gradient, correct? It gives you measure of change in potential with the change in distance, correct? Fine. Now, this potential gradient is having three formula as I written here. Now let us define the potential gradient. How will you give the definition? Very simple. Take this denominator as 1 unit, then this sigma will be VL1. Using that fact, you can define it this way: potential difference between 2 points separated by unit length or unit distance along the current carrying potentiometer wire is called potential gradient existing on that wire. I repeat, potential difference between 2 points separated by unit distance along the length of the current carrying potentiometer wire is called potential gradient existing on that wire. What about its SI unit? SI unit will be SI unit of voltage divided by SI unit of length. Voltage has SI unit volt, for length it is meter, so it is volt upon meter, volt upon meter. That is the SI unit of potential gradient. Got it? Fine. My dears, here sigma is constant. Why sigma is constant? Because EMF of the battery in the primary circuit is constant, resistance per unit length of potentiometer wire is constant, capital R resistance in the resistance box is constant, and this internal resistance of a battery connected in primary circuit is constant. Total length of the potentiometer wire is constant, correct? So under given conditions, these all values are constant, so sigma is constant. And when sigma is constant, you can write VL1 proportional to L1. VL1 proportional to L1. Instead of VL1, I have written here VL. Instead of L1, I have written L. So VL is proportional to L. VL is proportional to L. What does it indicate? What does this indicate? If this point is shifted on left side, length will decrease, potential difference will decrease. If you shift it on right hand side, then length will increase, potential difference will increase. I mean to say, this potential difference is directly proportional to this length, correct? This gives you working principle of potentiometer. How? I am showing you. When you change this length, this potential difference can be changed. So potential difference can be varied, can be changed. Not only that, we can measure it also, because that potential difference is this much, correct? Now all these values are known in laboratory, so ultimately by calculation you can find out this potential difference. So not only this potential difference can be changed, it can be measured also. That is how I gave you introduction of potentiometer. It is superior to rheostat. In case of rheostat, we can simply change the potential difference, but we cannot measure it. Here, not only we can change, we can measure it too, correct? Now, let us go for some 3 applications, 3 uses of this potentiometer in our syllabus. First is how to compare two given EMFs. Second is how to find out unknown EMF. And third is how to find out internal resistance of a battery, okay? Let us go for these uses one by one. First we go for comparison of two EMFs, comparison of two EMFs. And now you please consider this part of the circuit drawn below primary circuit. This part is known as, look here, secondary circuit. Okay. Now those two batteries whose EMFs are to be compared are to be connected here as per the diagram. Look, this is a first battery having EMF E1, this is key K1, this is sensitive galvanometer G1, and this is jockey connected with this sensitive galvanometer. Okay. Come on, for second battery EMF is E2, key is K2, sensitive galvanometer is shown by symbol G2, and this is jockey connected with this galvanometer. Got it? Fine. What you should do? Keep this key closed only. Throughout the experiment, keep this key closed only. But at present what we do? We keep this key open. So this battery is not there in the circuit now. Now close this key. So this battery is connected in the circuit. Fine. Now what you should do? You should connect this end with the jockey, and that jockey you should slide on the wire. Correct? When you make it touching with the wire, this galvanometer will give some deflection. But then what you have to do? You have to slide the jockey, you have to bring it to that particular position at which this galvanometer should not give any deflection. Pointer should remain at 0 position. Correct? Fine. Suppose that point is C1. Correct? Now tell me, why this galvanometer gives you 0 deflection? What does it indicate? And this is 0, deflection is 0, meaning thereby there is no current passing through this battery. Correct? There is no current passing through this battery. Otherwise, if current is passing through this battery, that current will definitely pass through the galvanometer, will definitely produce some deflection. But because there is no deflection, you must say that this battery doesn't allow any current to pass through it. Okay? When there is no current passing through any battery, that battery is said to be in the open circuit condition. Last time we had seen. And because right now there is no current through this battery is right now in open circuit condition. Here it is, open circuit condition. And suppose current passing through this battery, earlier it was I1 suppose, and because there is no current right now, I am writing I1 equal to 0, I1 equal to 0, correct? Just recall the equation of terminal voltage. What was that formula? V equals to E minus IR, V equals to E minus IR, correct? Now tell me, this I1 is 0 right now. There is no current passing through this battery, correct? So I1 is 0, put here 0. Then V1 equals to E1, V1 equals to E1 because I1 is 0. Now just speak reverse, E1 equals to V1, E1 equals to V1. What do you mean by E1? EMF of this battery. What do you mean by V1? It's a terminal voltage, and that terminal voltage must be equal to potential difference between these 2 points. Between which 2 points? Between points A and C1. But these 2 points are separated by distance L1, and potential difference between those 2 points separated by distance L1 we had earlier shown by this symbol VL1. So this V1 is nothing but VL1. How this E1 equals to VL1? Try to understand, my dears. Look here. When current is passing through this potentiometer wire this way, this end is positive and this end is negative. So this much length of the current carrying potentiometer wire will behave like a battery of certain voltage. Suppose that certain voltage, just assume say 5 volt, say 5 volt. So now this much length of the wire acts like a battery of terminal voltage 5 volt. That battery I am showing here. Look, suppose that battery is this, correct? Having terminal voltage how much? 5 volt. And this EMF is also suppose 5 volt. Just assume. If this is also 5 volt, this is also 5 volt, and for both the batteries, their positive terminals are connected here, negative terminals are connected here. So the situation is like this. Look, these 2 batteries have got equal EMF, positive connected with positive, negative connected with negative. So this is parallel connection and in an opposing manner. Now tell me, if this EMF is greater than this, current will flow this way. If this EMF is greater than this, current will flow this way. but just now you said there is no current passing through this battery. So neither current is passing this way nor current is passing this way, meaning thereby this EMF must be equal to this, correct? What is the potential difference between these 2 points? Potential difference between these 2 points separated by distance L1, it is VL1, and this EMF is E1. So this EMF, which is E1, must be equal to potential difference between these 2 points separated by distance L1, it should be VL1, correct? That's why E1 equals to VL1. I am writing here, E1 equals to VL1. And what is VL1? VL1 is, come on, sigma into L1. VL1 is sigma into L1, correct? Give it equation number 1. Now what you have to do? Take out this key and make this key close. When you have taken out this key is open now, this battery is removed from the circuit, and when you close this key, this battery is connected in the circuit. Tell me what you will do now? You will slide this jockey on the potentiometer wire, and you will find out one such a point C2 where this galvanometer should give you 0 deflection, correct? When galvanometer gives 0 deflection, such point is called null point or balancing point or equilibrium point. Null point, balancing point or equilibrium point, correct? Once you find out null point, you are supposed to find out the distance of point C2 from positive end of the wire, that is from point A. Find out distance AC2, let it be L2. This is called length of potentiometer wire which can balance this much EMF. This is that length of potentiometer wire which balances this much EMF, okay? Come on. Similar to this equation, now you can tell me instead of E1 what should I write? E2. Instead of V1, V2. Instead of VL1 I should write VL2. Sigma is constant. Instead of L1 I should write L2. Give it equation number 2. This is in case of balancing of first EMF. This is in case of balancing of second EMF. Okay, fine. Now just take the ratio. Take the ratio. This to this. E1 upon E2 will be equal to this upon this. Sigma sigma getting cancel. L1 upon L2. Here it is. L1 upon L2. Please remember this relation. E1 upon E2 equals to L1 upon L2. Now tell me how to compare two EMFs. Very simple. If you have done this experiment, you must have found the positions of these two null points, and correspondingly you must have found these two lengths. Okay. Suppose this length L1 is suppose 80 centimeter and length L2 is suppose 240 centimeter. My dears, remember only in Western bridge the total length is 1 meter, correct? But in case of potentiometer wire, the total length is nearly 400 centimeter. 400 centimeter. So you can consider this big amount of length also. Okay, fine. Suppose if L1 is 80 centimeter, L2 is 240 centimeter. Put it here. This is 80. This is 240. Come on. L1 is 80. L2 is 240. 80 3s are 240. So it is 1 upon 3. Transfer this E2 here. Transfer this 3 over here. You will get E2 equals to 3E1. E2 equals to 3E1. E2 equals to 3E1. What does it mean? That second EMF is thrice the value of first EMF. EMF of second battery is 3 times EMF of first battery. This is how you can have comparison between two EMFs, correct? Using potentiometer, correct? So this is the comparison between two EMFs done using potentiometer. How to get unknown EMF? Measurement of unknown EMF. How to get it? I am showing you. Purchase dry cell from the market, which we call pencil cell. Its EMF is 1.5 volt. We call it standard electric cell. Standard electric cell. A cell whose EMF is accurately known is called standard electric cell. Okay? Just use it here in place of first battery. When you use it here in place of first battery, this EMF is known to you. How much? 1.5 volt. Put it here, that battery, that standard electric cell, you must put it here, and then you should find out this corresponding length of potentiometer wire which can balance this much EMF. Okay? So this length is known to you. E1 is 1.5 volt. This length is also known experimentally, and then after the unknown battery whose EMF is to be found out, you should place here in place of second battery, correct? And then after, to balance that EMF, how much length of the potentiometer wire is required, that you can find out experimentally. Let it be L2. So value of L2 is known to you. Put it here. you know three values. You know E1 which is 1.5 volt, this L1 and L2 you know, you can find out E2 from this equation, correct. So, that is how we can find out unknown EMF also, correct. Now, my dears, one very interesting point in the entire working of this potentiometer, we have not discussed anything about use of resistance in the resistance box. So, you may have a question, what is the role of this resistance in the entire discussion? It has got very useful application, how we use the value of R in the resistance box. I am showing you. Use of resistance R in the resistance box. What is its application? What is its use? I am showing you. Tell me. Suppose the EMF which is to be found out is suppose very small EMF, correct? Then naturally for measurement of very small EMF, you need to be very accurate. See, we want to take the observations very accurately, but sometimes it so happens that the device, the instrument doesn't respond. For example, in laboratory, in case of potentiometer wire, we come across one specific problem. What is the problem? I am showing you. Suppose this length is 60 centimeter, okay, and here when you touch jockey, suppose this gives you 0 deflection, fine. Then if you slide the jockey, say slightly towards left hand side, suppose up to 59 centimeter, 59, then also it so happens that the deflection remains 0. And from here onwards, if you just slide it slightly towards right hand side, say up to 61, then also this deflection remains 0. So, what I mean to say, within the range of 59 centimeter to 61 centimeter, if you slide the jockey, then the deflection remains 0. So, we are not in a position to find out the exact position of a null point, and unless and until you find out the exact position of null point, you cannot measure this length accurately. And if the lengths are not measured accurately, then that unknown EMF, if it is very small, cannot be measured accurately. That is for sure, correct. Then what to do? Whenever you come across such a problem that when you slide the jockey, then also deflection is remaining 0 only, at that time remember the sensitivity of potentiometer wire is very low sensitivity. You need to increase its sensitivity. What to do in practice to increase the sensitivity? I am showing you. Recall the formula of sigma. Formula of sigma was E rho upon R plus L rho plus R. Here it is. Sigma equals to E rho upon R plus L rho plus R. Whenever you come across this low sensitivity of potentiometer wire, whenever you come across this problem, you remember you need to decrease the value of sigma considerably. You need to decrease it considerably. You need to make it of the order of millivolt per meter or microvolt per meter. Millivolt per meter or microvolt per meter. Millivolt means 10 raised to minus 3 volt and microvolt means 10 raised to minus 6 volt. When you decrease the value of sigma considerably, at that time what happens? Potentiometer wire becomes highly sensitive, and then after if you slide the jockey very slightly also, then also this galvanometer will give you big deflection, okay. And when the sensitivity is very high, you will get one and only one point as a null point, correct. And if you just locate the position of null point exactly, then you can measure this length also very exactly, and then these lengths are measured accurately, then naturally unknown EMF, if it is very small, can also be measured accurately, correct. So, what I mean to say, whenever sensitivity of potentiometer wire is low, you need to increase it, but for increasing the sensitivity of potentiometer wire, you need to decrease the value of sigma. But just look at this formula, E is constant, rho is constant, L is constant, rho is constant, small r is constant, and then also you need to decrease the value of sigma. The only option left with us is to increase the value of resistance in the resistance box properly to the high amount, such that when this increases considerably, this will decrease considerably, and when the value of sigma is of the order of millivolt per meter or microvolt per meter, at that time sensitivity of potentiometer wire is very high, and then you can locate the position of null point very accurately. Then after you can measure this length also accurately, and then you can measure unknown EMF. If it is very small, then also you can measure it accurately, okay. So, this is the definite use of resistance in the resistance box. Okay. Come on, my dears. Last time we had talked about potentiometer, correct? And using potentiometer, last time we had found out EMF of unknown given cell, and also we had compared two EMFs of two given cells, correct? Now, if those two cells, if you are connecting in an assisting manner or in an opposing manner, then how can you compare their EMFs? I am showing you. Look, first of all, talk about assisting or helping condition. Assisting or helping condition. Now, what is that type of connection? I am showing you. If you got two cells and if you are connecting their unlike poles together, then that connection is called helping or assisting connection. For example, here you can see negative terminal of first cell is connected with positive terminal of second cell. Here negative and here positive. So, you can say unlike terminals are connected together, correct? Fine. Now, why this connection is called assisting or helping connection? Because here both the EMFs help each other, and that is why the resultant EMF is found to be summation of individual EMFs, E1 plus E2. Because the two EMFs are helping each other, we call this connection or condition as helping condition or assisting condition, correct? Fine. What about opposing condition? Look, here you can see negative terminal of first cell is connected with negative terminal of second cell. Here also negative, here also negative. So, you can say like terminals or like poles are connected together, then that condition is called opposing condition. Why opposing condition? Because at that time both the EMFs oppose each other, and that is why the resultant EMF is bigger minus smaller, bigger minus smaller. Okay, fine. Now, last time we had obtained this small equation, remembered? E1 equals to sigma L1. What was E1? EMF of first cell connected in the secondary circuit of potentiometer. Remember? What was sigma? Potential gradient existing on current carrying potentiometer wire. What was L1? It is that length of potentiometer wire which can balance this much EMF, correct? And for the second cell we had also obtained E2 equals to sigma L2, correct? And now tell me, in an assisting manner, what is the resultant EMF? E1 plus E2. So, just add these two, find out E1 plus E2. It is this plus this, so it is this plus this. When you take sigma common, it will be into bracket L1 plus L2. What about opposing condition? For opposing condition, the resultant EMF is E1 minus E2. So, it is this minus this. So, it is this minus this. Again you can take sigma common, inside the bracket L1 minus L2, L1 minus L2, correct? Now, just take the ratio, this upon this will be equal to this upon this, E1 plus E2 upon E1 minus E2, here it is, and that equals to this upon this, sigma sigma getting cancelled, left is L1 plus L2 upon L1 minus L2, correct? Now, this total length I just indicate by new symbol, suppose L3, and this length I just indicate by new symbol, say L4. Here L3 equals to L1 plus L2, L3 equals to L1 plus L2, and L4 is equal to L1 minus L2, L4 equals to L1 minus L2, correct? So, tell me, this is the resultant EMF in the assisting condition, this is the resultant EMF in the opposing condition, and that two EMFs you can compare by finding this ratio L3 upon L4. Simple. How will you interpret this length? This L3 is that length of potentiometer wire which can balance this much EMF, that is E1 plus E2. What is L4? It is that length of potentiometer wire which can balance this much EMF, that is E1 minus E2, correct? Now, from these two lengths, if you want to compare E1 and E2, how would you find out ratio E1 upon E2? Very simple. Take a componendo in the numerator and dividendo in the denominator. If you do that, then just take it here, addition of these two, componendo in the numerator, meaning thereby this plus this. So minus E2 plus E2 will cancel, E1 plus E1, that is 2E1. In the denominator you are supposed to take the dividendo, then it is this minus this. Come on, E1 minus E1 getting cancelled, this minus minus plus E2, E2 plus E2, that is 2E2, correct? Do the same thing on right hand side here. In the numerator, when you take componendo, it will be L3 plus L4. In the denominator, dividendo, then L3 minus L4, correct? Now these 2 will cancel. So giving you E1 upon E2, it will be L3 plus L4 upon L3 minus L4. So if you know L3 and L4 values, you can put them here, and from that two values also, from those two values also, you can find out this ratio, and ultimately you can compare these two EMFs. Okay, fine. Come on, my dears. Now we go for third application of potentiometer. Last time we had seen already two applications. First was how to compare two given EMFs, correct? Second was how to find out unknown EMF. And the third we see right now, it is about how to find out internal resistance of a given cell using potentiometer. Okay, fine. Just to find out internal resistance of electric cell using potentiometer, you please consider this circuit diagram. See, last time also we had drawn complete circuit diagram of potentiometer, correct? In that I had shown two parts. One was upper part, which was known as primary circuit. Another one was lower part, which was known as secondary circuit. Okay? Here, the primary part is to be kept as it is without any change. Look here. The same primary circuit I have shown here, in which you will find one battery, one key, one resistance box, and one long and straight uniform resistive wire, correct? Fine. Now when you place this key, then circuit is closed, in which current passing through all the components would be same, let it be capital I. And that direction you can show away from this positive terminal in the outer part of the circuit, then that current will be flowing through this potentiometer wire also. And when current is flowing through the potentiometer wire, we will have some potential gradient existing on the wire. And that potential gradient was last time shown by symbol sigma, and its formula was, remembered, E rho upon capital R plus L rho plus small r. Same formula written here, correct? Now just give me identification of each symbol. Capital E is the EMF of the battery connected in the primary circuit, correct? What is rho? It is resistance per unit length of potentiometer wire, correct? Last time I had given you one warning, remembered? This rho is not resistivity, no. Though symbol is same, but right now it is not resistivity, it is simply resistance per unit length of potentiometer wire. Its unit is ohm upon meter, correct? What about capital L? It is total length of potentiometer wire. For 1 unit length, if resistance is rho, for L amount of length, total resistance would be L into rho. So this L into rho indicates total resistance of potentiometer wire. What about capital R? It is the resistance taken out in this resistance box, or you can say it is the external resistance connected in series with potentiometer wire, correct? What about small r? It is internal resistance of this battery connected in primary circuit, got it? Fine. Now, in addition to this primary circuit, what extra part we have to connect, that is shown below this, and in that secondary circuit, now we are making little change. Earlier we had connected two cells, now we just connect only one cell, say first cell, and that cell is to be connected in this manner. Here E1 indicates the EMF of first cell, small r1 indicates the internal resistance of first cell, which we have to find out, correct? With an intention that you should not be getting confused, I am not using here small r, I am using here r1, because if I write here small r, somebody will be misguided that we are finding this internal resistance. No, we don't have to find out internal resistance of this battery connected in primary circuit. No, at present we are finding internal resistance of this cell connected in secondary circuit, okay, and that is first cell. So I am just using symbol for internal resistance as small r1, okay. This we will find out, r1 we will find out using potentiometer. Now just parallel to that first cell, we are supposed to connect another resistance box and key as per the diagram, okay. And then this parallel connection, this loop is now connected with a sensitive galvanometer, say G1, and further it is to be connected with a jockey, correct. So this is how you should make the connection. Throughout the experiment, this key is to be kept closed only, okay. Now tell me, initially if you keep this key K1 open, because you are keeping it open, then this resistance box will not be connected in the circuit, correct. So at that time you are connecting only the first cell, fine. And then after, what you should do, you should slide this jockey on the potentiometer wire, and you should find out one such a point, for example say C1, at which when you touch the jockey with the potentiometer wire, this galvanometer should not give you any deflection, correct. When there is no deflection in the galvanometer, meaning thereby there is no current passing through this battery, correct, then only there is no deflection here, correct. Had there been some current here, that current would have flown through the galvanometer, it would have produced some deflection, but deflection is not there, so there is no current passing through this battery. And if no current is passing through this battery, it is said to be in the open circuit condition, correct. And at that time its EMF will be getting balanced by how much length of potentiometer wire I am showing you. Once you get this point where this galvanometer gives you zero deflection, that point is called null point or balancing point or equilibrium point, correct. Once you get this null point, then you are supposed to measure its distance from this positive end of the potentiometer wire. That is, you must measure now this length AC1, and that length AC1 is shown by symbol L1 in the circuit, okay, fine. Now you just measure this much length, and now tell me, last time we had obtained one very small equation, E1 equals to sigma L1, correct. What was E1? It is EMF of the first cell connected in the secondary circuit. What is sigma? Potential gradient existing on potentiometer wire, and this L1 is that length of potentiometer wire which can balance this much EMF, correct. Why this much length is said to be balancing this EMF? That I had explained last time. Once again let me remind. See, when there is no current here, meaning thereby the potential difference between these two terminals and potential difference between these 2 points must have been equal, and for both the potential differences, their positive ends are connected here, negative ends are connected here. And tell me, when there is no current through the battery, whether you call terminal voltage or EMF, both of them are same in the open circuit condition, then that EMF will be equal to potential difference between these 2 points, correct, fine. And what does sigma indicate? It is potential gradient, but what does it indicate? It indicates potential difference per unit length. Per 1 unit length, if potential difference is sigma, then for L1 amount of length, what was the potential difference? Sigma into L1, sigma into L1. So this potential difference and this EMF, they have become equal, correct? Fine. Now you do one thing, you just keep this key closed now, make this key K1 closed, just close the key K1. When you close it, look here, it will so happen that some current will pass in this loop. Let it be I1 dash, correct? I am writing here symbol I1 dash, fine. Now that current is passing through this battery, and when current is passing through the battery, it is said to be in the closed circuit condition. Right now some current is passing, so it is not in open circuit condition, now it is in the closed circuit condition, correct? Why I am showing the symbol I dash? Because it is not I. I is the current passing through primary circuit, correct? Here I dash is the current passing through this cell, correct? And why I am using symbol I1 dash? Because it is passing through first cell, that's why. In case of second cell, you may show I2 dash, got it? Fine. Now tell me, at that time, after placing this key, what you have to do? You have to slide this jockey once again on the potentiometer wire, and then after you are supposed to find out one such a point, say C1 dash on the potentiometer wire, where if you touch the jockey, then this galvanometer should not give you any deflection, correct? Now that point is suppose C1 dash, and once you get that null point C1 dash, then after you are supposed to measure its distance from this positive end of the potentiometer wire, that is distance AC1 dash. Let it be L1 dash, okay? Now let us see, this much length of potentiometer wire, balance is what? Let us see. Look, because there is some current passing through this battery, now the potential difference between these two terminals of this battery will be terminal voltage. Potential difference between two terminals is called terminal voltage, that is true. But right now that terminal voltage is not equal to its EMF because the battery is in the closed circuit condition, correct? Now this terminal voltage between these 2 points, for the first cell I am showing by symbol V1. V1 is the terminal voltage of first cell. Now that potential difference will be just equal to potential difference between these 2 points separated by distance L1 dash, correct? What is sigma? Potential gradient. What does it indicate? It indicates, come on, potential difference per unit length. Per 1 unit length, if potential difference is sigma, then for L1 dash amount of length, what will be potential difference? Sigma into L1 dash, sigma into L1 dash, sigma into L1 dash, correct? So potential difference between these 2 points and potential difference between these 2 points must have become equal, correct? And potential difference between these 2 points is nothing but terminal voltage of this first cell, let it be V1, correct? Fine. Tell me, what is L1? It is that length of potentiometer wire which balances this much amount of EMF, correct? And what is L1 dash? It is that length of potentiometer wire which balances this much terminal voltage. I repeat, what is L1 here? It is that length of potentiometer wire which balances EMF of first cell. What is L1 dash? It is that length of potentiometer wire which balances terminal voltage of first cell. And tell me, this cell is in the closed circuit condition. For any cell in the closed circuit condition, its terminal voltage is smaller than its EMF. So here this terminal voltage is smaller than this EMF, meaning thereby this length must be smaller than this length, that is L1 dash must be smaller than L1. Look in the diagram, this length L1 dash is smaller than this length L1, correct? Just take that care, you must show L1 dash smaller than L1, correct? Fine. Now, for a cell which is in the closed circuit condition, and if the current is going away from positive terminal, then that battery is getting discharged, correct? For any battery which is getting discharged, what is the relation between terminal voltage and EMF? Have you not remembered? V equals to E minus IR, V equals to E minus IR, V equals to E minus IR. But I am making little change in that, symbols. Here I am showing terminal voltage of the first cell, let it be V1. E1 means, come on, EMF of the first cell. I1 dash is right now current passing through the first cell, and R1 is the internal resistance of first cell. Okay, fine. Now this V1 as it is, E1 as it is, minus as it is. What is I1 dash? It is the current passing in this single closed loop. Okay, fine. Mind well, when you balance this terminal voltage between these 2 points, at that time current passing through this part and this part has become 0, but current passing through cell has not become 0. That current is I1 dash, which is different than this current. Okay, fine. Here current is definitely passing, here current is definitely passing, and that current is I. Okay, and so far current in this loop is concerned, it is I1 dash. Okay, there is no current here and there is no current here. Got it? Fine. Now in a single loop, if you got current, then according to Ohm's law, the formula of that current is effective EMF divided by equivalent resistance. Effective EMF divided by equivalent resistance. What is effective EMF in this loop? It is E1 divided by equivalent resistance. But right now we find series connection of this and this resistances, and have you not studied in the same chapter about law of series connection of resistances? What is equivalent resistance in that case? Simple summation of individual resistances. So just add these two. R1 dash plus R1 will give you equivalent resistance in this loop, correct? It is a series connection of this and this, fine. And that effective EMF upon equivalent resistance will give you current, and into small r1 as it is. Just simplify now. Take LCM, it will be capital R1 dash plus small r1. This will be multiplied here. So E1 into capital R1 dash plus E1 into small r1 minus E1 into small r1, correct? This is also E1 into small r1, this is also E1 into small r1, this is plus, this is minus, getting cancelled. Now left is capital V1 equals to capital E1 into capital R1 dash upon capital R1 dash plus small r1. Same formula I have written here, same formula. Okay. Now just transfer this and transfer this over here, then it will be R1 dash plus R1 will be E1 R1 dash upon V1. Find out R1, because we want internal resistance of first cell, make it subject of the equation, transfer this term. And after that you can take R1 dash common, inside the bracket it will be E1 upon V1 minus 1, correct? Now R1 dash as it is, what is E1? E1, that formula we had obtained last time, it was sigma into L1. E1 is sigma into L1, correct? What about V1? V1 formula we have obtained right now, it is sigma into L1 dash. V1 is sigma into L1 dash minus 1, correct? Now sigma will cancel, giving you R1 dash into L1 upon L1 dash minus 1. Now tell me, what is capital R1 dash? It is the resistance kept in this resistance box, which is connected in parallel with the first cell. That value, if you know, you can just put it here. And what about length L1? It is the length of potentiometer wire which can balance EMF of the first cell. Okay. What is L1 dash? It is that length of potentiometer wire which can balance the terminal voltage of first cell. Okay. And I told you earlier, this length is smaller than this. So denominator is smaller than numerator, then this ratio will be greater than 1, and so this bracket will be positive. This is already positive. Multiplication of two positive values will give you positive value. Okay. As such also resistance must be positive, correct? Remember, this length is smaller than this length. Okay. Similarly, if you want to find out now internal resistance of second cell, what you can do? Instead of first cell, you may just connect here second cell with EMF E2 and internal resistance R2, correct? and there if you are connecting another resistance box in parallel like this, and there if you are keeping the resistance say R2 dash, then similar to this you can just tell me the formula. In that case, instead of small r1 you can write small r2, instead of capital R1 dash you may write capital R2 dash, and into bracket instead of L1 you may tell me L2, and instead of L1 dash it will be L2 dash minus 1 as it is. Okay. Tell me what is L2? It is that length of potentiometer wire which can balance EMF of second cell, correct? What is L2 dash? It is that length of potentiometer wire which can balance terminal voltage of second cell. Got it? Fine. So this is how using potentiometer we can find out internal resistance of a given cell.